Okay, cool. Yeah, so this is how to decide which model to use in machine learning, and just like a raise of hand, like how many people have done stuff in machine learning, just so. Okay, cool. Yeah, so this is like the idea for this is kind of like I know what machine learning is. I have a task that I think would be good for machine learning, and I have the data for it, but I don't necessarily like know which steps to take next. And traditionally, that's really just finding out which model to use, and that can be a daunting decision to make if you don't have a lot of like prerequisite knowledge for really analyzing and like being able to differentiate between models. So, how do I do this?
Wait, try now. Try one more time.
Is it just that fun? All right. Well, anyway, that's me. I work at Funkhaus. I like machine learning. I have experience in audio information retrieval and natural language processing, and that's my email in case you want to get in contact with me. Yeah. And yeah, so just the agenda, just a quick overview of what machine learning is and how that might be different from your normal kind of programming model. And what exactly is a model? Start out with that. Strategies for picking a model, and then learning how to evaluate and identifying some sources of error that can come from your model when you're developing machine learning. And also, if anybody has questions during this, just raise your hand, because I'd rather you not be confused along the way and not be able to, pick up information as we go. So, yeah. So with traditional programming, you have some sort of task, and that might be like sorting an array. And the solution for that task is really simple. You just simply put in the instructions to sort that array, and every single time your function will do exactly what it's supposed to do. And with machine learning, though, you don't really know what the solution is or necessarily how to find it. All you have is data that's represented by, I guess any kind of data that you're going to be working with, and then the associated output that you would like from your machine learning program, and that's associated with the inputs. And so with machine learning, your inputs and outputs might not really well be understood. So that can be like, say you're working with text documents. Well, you don't always know all the different text that's going to appear in a given document. But with like traditional programming, you can ensure that the inputs to your program are going to be the exact same every single time, or at least structurally. And also with machine learning, you might not know what your outputs are. You could be doing unsupervised tasks, or you could be doing supervised tasks where you're directly trying to predict something. And your outputs could be predicting a quantity, predicting a class, all sorts of things. And I mean, the biggest difference is that with machine learning, your machine learning algorithm produces the solution. You don't directly learn the solution to your task. So yeah.
Could you really quick go through just a really quick example of what those things are like illustrating there?
Yeah. So inputs, like for the sorting an array, an input would be like the array itself, and the program would be the function to sort the array, and what you get out is the sorted array itself. But with machine learning, your inputs are going to be your kind of training data set, and then your machine learning program generates the actual program that does the task that you're looking to do. So this could be, spam classification, and your inputs are your like spam emails, and the outputs are the correct labels for those spam emails, so if they're spam or not. And then what outputs is a program that can actually determine if things are spam or not spam. Yeah. And then this is kind of just the general machine learning setup. So your original data, it's going to be like your spam emails, and then you separate that into training and test data, and then from the training data, you separate it again into training and validation data. And when you're developing your machine learning model, figuring out what models to use and things like that, you're only really working with your training data and your validation data to determine that. And then once you're kind of done tuning and evaluating all of it, you use your testing data to give like a final determination on your model if it's good or not. Once you've kind of done this part, then you kind of have to throw all of your data away, so you really leave using the testing data to last. Because if you use your testing data at all during your tuning, training, evaluation portion, then it's going to introduce bias into your final model. So really what ends up happening is you train your model to your data itself, and then it won't really perform well in the real world. And you want to go to the next one? And what we're going to be focusing on today is just like this training, tuning, evaluation part of the process. And that's where your that's where your performance gains are going to come out of, is making good decisions in that portion. Yeah. So you can kind of think of a model as a black box, kind of. You know, you put in your input and then you get some sort of output. You're not necessarily concerned with the exact computations that happen inside of that black box. And generally in machine learning, you think of it as taking an input vector x, and that vector, you know, for spam emails can just be a vector of word counts in that email. So like the first integer is how many times the word the occurs, and then the next is associated with another word, and so forth. And that just gives us an output of y, and that can, you know, either be a quantity. So if you're doing regression, it'll be an actual number, or if you're just doing some sort of classification, so if it's spam or not spam, that can be a binary number. It really depends on the task that you're working on. And yeah, given a set of data x, it generates a solution that correctly predicts the corresponding labels y. And every single model makes assumptions about the data itself. That's kind of that's where the power of a model lies. And it's using those assumptions to generate a solution to your problem. And we'll get into some of those assumptions and see how that can impact performance in the model itself, and what happens when your assumptions about your data aren't really validated in the data itself. And there are many types of models, so like probabilistic, nonlinear, and all these things kind of relate to how the data is distributed and what kind of assumptions you're making about the data itself. So yeah. So just two simple examples. Naive Bayes is kind of the go-to probabilistic one. And its assumption is that the features are independent of the label. And what that translates to in the actual model itself is that you don't really pay attention to the label itself. Well, you only look for correlations between individual features and the label. And it uses the probability of the feature given the label. It's really good for high variance data because since the model is purely probabilistic, it's insensitive to outliers in the data, and because of that, it handles data that has high variance very well, as opposed to something like the Perceptron, which is very sensitive to outliers in your data set, and depending on those outliers in your data set, you can come to very different models, or very different solutions, I should say. And with the Perceptron, the only assumption is that the data is linearly separable. And while that's kind of a strong assumption to make, that there is like something that linearly separates your data, so meaning like if you plot your data, there's a clear line that you can draw that can separate your data into two discrete groups. And that's a pretty, you know, large assumption to make about your data, but in practice that translates to actually a pretty low assumption, and it produces a model that has low bias, but is very sensitive to changes in your data. Yeah, Jeremy?
It's like distinguishing between cats and dogs because they can only be either cats or their dogs. Use more here.
For Perceptron?
Yeah.
Yeah, definitely. It's definitely for binary classification, and I don't think there's a way to do it with regression. But yeah, exactly. It's really just a binary yes or no, kind of flicking a switch on and off. And the Perceptron just determines how much force is required to, you know, flip that switch on or off, basically. Yeah.
I think you mentioned that, like, with a Perceptron, you could possibly come out with a different, like,
Yeah.
if you do it different times, it could possibly come out with different solutions versus naive Bayes, like, you will get the same solution every time.
Yeah.
Is there a word for, like, how, like, the measurement of that is on a model? Like, how likely it is to come out with different solutions versus, like...
Well, really, that's the variance of the model. So it's how much does your model vary when your data varies. is a way to think about it. And there's a good GIF example of like how you can kind of see that sensitivity come out when the model is training itself. Yeah. So this is that example actually. So this is the Perceptron when it's training. So how the Perceptron works is it like randomly initiates a solution, let's say, and the solution is just this line that separates your data. And once it's generated that, it determines if, using that solution, it got any predictions wrong. And if it does, it has a really easy way, or clear way of kind of correcting itself. Check again if I like got any predictions wrong, and then keep correcting myself until I get all my predictions correct. And once it gets all the predictions correct, it's done. It's found its solution, and it's ready to move on. And what you see is like, it starts right there, and then it slowly moves like that, because you can see that it gets these couple predictions wrong initially. And then once it passes this point right here, it's done. It's figured out its solution. And you can kind of see that this is pretty sensitive to variance, because if there was a point right here, it would be a vastly different solution than what it is now, because it would have to figure out that the line goes right there. And also, if this one point wasn't here, then it would stop a couple iterations before it is now to find that solution. Yeah, what's up?
Is the Perceptron linear?
It can be nonlinear, but generally speaking, when you're talking about the Perceptron, it is a linear, like it's a linear classifier. There's ways to not like hack it, but like kind of tricks to make it nonlinear. And it's linear, meaning that like the solution that it finds is linear. It's just a straight line. Yeah. What's up?
So if you were to try to run this and it won't work, will the model set something out like, yeah, no, I'm not going to work?
Yeah. So if there was a blue point right here, then it would fail to like converge on the solution. So this is an iterative process. So it says like, okay, I have a solution. Let's see if I predict every point right. And if it doesn't, then it's like, okay, I'm going to correct myself a little bit and then try again. And then just keep repeating that process until it correctly predicts every single point. And so if it's impossible to linearly separate this data, draw a line that separates the two groups, then it will just keep trying to correct itself and find a solution. Yeah, what's up? I mean, this is just a random example. It's on flower data, so this is like the length of septal, I guess, and then petal length. But really, I mean, this is just easy to visualize because it's two things. Typically, when you're doing machine learning stuff, like say a spam email, you have to consider every single word. So really, every single point is in like an n-dimensional space, which you can't visualize. But here, it's only a two-dimensional space, so it's easier. Yes.
You mentioned there were 3 phases to the machine learning process.
Yeah.
Is this a visualization of just the training phase, or is this training plus what was it called? Verification?
Validation. Yeah. So this is just training.
Okay.
Mm-hmm. Yeah, and there's I mean, it gets kind of complicated because in training there is like error associated with it. So every iteration of this algorithm, it finds the error associated with it is how many points it got wrong, basically. And as long as it kind of converges on a solution for this model, you don't really care otherwise. Yeah. Okay. And then just before we look at the naive Bayes one, just a reminder of what Gaussian distribution looks like, because you kind of need to know. A distribution is Gaussian if it can be described by the mean, so in this case 0, and then also the variance or standard deviation, which gives you these nice boundaries. And the percentages are like how much of the data is within this standard distribution, or yeah, in this standard deviation, and then within the second and third and so forth. So the idea being that most of your data is going to be centered around the mean, and then it kind of spreads out in lesser quantities as it goes out. And then if you want to go to the next one, you can kind of see. So this is the naive Bayes model. These are each Gaussian distributions, just two-dimensional ones. And the center is the mean of each of them. And you might not be able to see back there, but you get blue shading as you get into the center, and then red shading. And that shading is the probability of one of these points belonging to that class. So if one of these points is like closer to here, you can calculate the probability that it belongs to this class and the probability that it belongs to this class, and see that probability is much higher, so it lies there. And you know that this model is low variance because everything, it assumes that your data is Gaussian distributed. So with a perceptron, if there was like another point here, then you'd have to find a very different solution. But with this, it just says, you know, okay, these points are very far from the mean, so they should have little impact on the actual decisions that I make about data. And so that means that it's pretty insensitive to changes in your data itself, as long as the means of these distributions don't change, really. So yeah, just kind of getting back to the question, how I know which model to use. First, it really depends on what you're trying to predict, you know, a class, a quantity, a ranking. Because if you're doing class, then things like naive Bayes or Perceptron would definitely be more appropriate. But if you're looking for a quantity, you're going to have to use a regression model because you're trying to predict an actual kind of numerical value associated with something. And that's a whole kind of another class of models. Or a ranking is, you know, you can, it's a more involved, well, different set of models, really. It's a different process. And then, you know, what is your data like? The amount of data that you have is really important. You know, with Perceptron, it really works well when you have large amounts of data because it's so sensitive to the data you present to it. You want to have a good coverage over all the different data points that might show up out in the wild. So it knows how to handle those, and it's kind of seen them before. But if you have a small amount of data, then something like naive Bayes will get you a better solution. Because as long as it has a sense of, you know, what the means in your data are, then it can kind of figure things out. And yeah, I mean, the format also, that's kind of associated with, you know, how much your data varies and things like that. But yeah, and then just kind of how you represent your data. And then also, what kind of assumptions can you make about your data? Do you know, if you know if it's linearly separable, then you might as well use a Perceptron or SVM. And if you know it's normally distributed, then you know that you should, like Gaussian Bayes would, or naive Bayes would be an appropriate model to use with that. And every single model has its own assumptions, and you can kind of look them up and see what fits your data and your problem. Really, it all comes down to knowing your data and your problem more than anything else, because there's information available for you to kind of pick and choose and figure it out what model to use. And this is a good like beginner resource. This is on scikit-learn's website, and that's a Python library for machine learning. And it just kind of walks you through, you know, how much data you have, what kind of task you're doing, and then points you in the direction of models that you should try using to begin with. And then from there, it kind of also gives you pointers on what other models to use, you know, if what you're using doesn't work. But yeah, there's just a lot of good resources online to figuring this kind of stuff out. And depending on what kind of task you're working on, people have kind of figured out already what the best models to use are. So looking on the internet and looking at research that's already been done is a really good resource for that. And then, yeah, getting to evaluating a model. So for model error, well, you have to think about all the different kinds of error that can show up. So you have your model, you put in a piece of data, and you get a prediction. That can either be true positive, meaning that your prediction was correct and it should have been correct. It's false negative, meaning that you correctly predicted that like it's false, so you correctly predicted that you know, spam is spam, or that not spam is not spam. And then a false positive, meaning that you predicted something was correct, but actually was not correct. So you predicted spam was not spam, but actually was spam. And then a true negative, meaning that like you correctly predicted that it's negative. And then, you want to go to the next one? And then these are the kind of bread and butter of evaluation metrics, precision being the number of correct predictions divided by the number of predictions made. So that's just, I mean, you take all of your, yeah, I mean, that's the easier one. That's one that I have a better time understanding. And then for recall, the number of predictions divided by the number of correct possible predictions. So the example that I like to think, or to use when thinking about this is like search results. So say you query, I don't know, scary movies, and you know that these 10 movies are supposed to be like the top 10 search results returned to you by your machine learning algorithm. Precision would just be, of the 10 results returned by your algorithm, what percentage of those results are true or are correct. But with recall, it's what percentage of those responses returned to you by your machine learning algorithm are correct out of all the possible correct ones that you returned. So it's not constrained to that top 10 ranking, you know? So in your data set, you say have like 30 movies, or I guess just like 10 exactly, but your machine learning algorithm only returned to you 2 true ones. So precision would be, you know, 2 divided by 10, but then recall would be, well, I guess it's not a good example, but it would also be 2 divided by 10. And that diagram gives you a good idea of, you know, the differences between the two. But when evaluating a model, it's really important to be aware of both of these, and which one is more important is really related to the kind of problem you're working on. So precision is more important when you want your every prediction to be correct, and then recall is more important for things like rankings, where you want every correct possibility returned as correct, you know? So yeah. And then just some other evaluation metrics. F1, it's just a weighted average of precision and recall, so it kind of takes into account both. So you can't, you know, your precision score can't be super high and your recall score be super low, and then your F1 will kind of balance the two out. ROC AUC is good for evaluating rankings. It really rewards for pushing highly, like for search engines, it rewards the program for pushing relevant recommendations to the top of the ranking, as opposed to, you know, randomly dispersing them in your ranking itself. And then entropy is good for certain models like decision trees and random forests, and yeah, other stuff like that. And there's a number of other evaluation metrics that are more dependent on the model itself. Yeah.
So these are essentially the functions that you use to determine while you're training it, like what the measure what you're measuring on for correctness.
Yeah, well,
sort of.
Yeah, so you train a model, and then once the model has been trained, you show it your validation data set, and then you generate these scores from your validation data set. So they are what tell you basically if your model is a good model for what you're working on or not. You know. Yeah. And then just look at some of the sources of error. So now you have metrics to determine that there is error present or not present. And then these are kind of the sources of those error. So bias, first of all, the bias is related to the assumption that your model makes. It's the model's bias towards a specific solution. So with a perceptron, it's biased towards, you know, finding a linearly, way to linearly separate the data, but it's biased in that it has to be linear, you know. So if your data is not linear, or it is impossible to linearly separate it, then you're going to get a lot of error due to bias because it just can't use the solution that it wants to use. Variance, so if your data has a very high variance, so every data point is going to differ from each other one a lot, so that Gaussian distribution is really flat, kind of. Then if your model can't account for high variance very well, then you're going to get a lot of error associated with it. So with the Perceptron, you need a lot of data in order to get kind of a stable solution, because if your data is high variance, then you need to get a good coverage over kind of every possible data point you might see out in the wild. But if you're using something like naive Bayes that is really kind of insensitive to variance in your data, then you won't really get a lot of error due to variance. And then noise is just kind of, like the exact definition is like two data points that have different labels even though they are the same point. So it would be like you have two identical emails, but one label is not spam and the other label is spam. Like logically that just doesn't make sense. And there's no real way to account for that in your model itself. So in order to account for noise in your data, you just have to get better features or ways to describe your data, or just get more data points itself. Yeah. And then this is also kind of what low variance and bias kind of looks like. So this is, your model really wants to use this one solution that's up here, but the right one is right there. And it's able to accurately use that solution. All the data points are really close to each other. And then high variance is, it has like a good solution to it, but it's really sensitive, so it kind of flies all over the place. That's just another way to look at it. Yeah. And then that's just the math explanation for it. I won't really get too into that. Here we go. Yeah, and so, what I've said is like there's some models that handle variance really well, and then there are some models that handle bias really well. So you might think like, oh, of course, I should just pick a model that handles both of them really well. You know what I mean? But it's not that easy necessarily, because you can do things. So if you have a lot of error due to bias, there are certain strategies that you can take to reduce that error due to bias. But any strategy you make to reduce bias inevitably increases the error due to variance and vice versa. So one of the goals of machine learning is to really find this sweet spot of model complexity and minimizing all error. So yeah, that's just something to consider.
Is variance a property, when you're talking about it in this
Yeah.
context, it is a property of the model you're choosing? Like some models have different levels of variance?
So it's a property of first the data, because going back to the email example, emails can have any number of words in them. And so a representation of an email is going to look very different from email to email, right? And your model is directly a result of your data. So your data generates your model. And so if your data has high variance, then your model will vary also as your data varies, and certain models will vary more or less depending on how the model is set up. And so diagnosing it, it's really just, you can actually do the math and figure it out, but just knowing your data and how it's distributed, just knowing the assumptions of your model, and if it's a strong assumption, then it might be very easy to see, okay, my data is violating that assumption, so I should probably try something else. Always getting more data, that can't really hurt, and can definitely help with problems with variance and noise. And yeah, also just a point, on certain models there'll be parameters on how the model behaves during training, and you can tune those parameters as much as you want, but it's not really going to help a whole lot. You really have to change up either what your data looks like or what your model actually is to get to a better solution. Yeah. This is not. Oh, okay, yeah. So for variance, or strategies for solving these sources of error for variance, it's just try a model that's less sensitive to variance, so something like naive Bayes or something like that. Also, collecting more data can help with that, because you'll get better coverage over all the data points that you might see out in the wild. Data augmentation is a strategy for that, which is just taking existing data that you have and tweaking it so that you get more data, generate new data out of the data that you already have. So an example of that is if you're working with image data, say classifying handwriting, so you have a bunch of photos of just somebody writing the letter A. Data augmentation for that could be like just rotating the image like a certain number of degrees and then generating a new image out of that. Because an A like 5 degrees to the left should still be an A, you know what I mean? And then bagging is another strategy for it, but that's for another talk. And then bias, visualizing your data is a really helpful way to do it, or a helpful like thing for diagnosing a bias problem, because you can kind of see how things are distributed. If your data is low enough dimensionality, then you can see if it's linearly separable, and just kind of get an idea of what's going on under the hood. And then, just trying different models that better fit the assumptions that you want to make about your data better, and then boosting also. And then noise, just adding more features and recollecting your data, because your process of collecting your data could have been flawed, and that's why you have a ton of problems and a ton of noise. And then if you want to learn more about boosting and bagging, I had a couple links there. Yeah. And yeah, just some resources. And yeah, that's it. Yeah, cool. So thank you. Yeah, it does fit into the models I'm talking about, but there's a bunch of, for that task specifically, there's some intermediate steps that can have a huge impact on it. So one of those being, separating a sentence into its like pieces of a sentence, so like verb, noun, and getting that hierarchical structure of the sentence itself can really influence determining what the sentiment is in the sentence itself. So a lot of times, it kind of comes down to those other like auxiliary portions of it. And then the model itself, once you kind of have all that in place, it's usually pretty easy to see what it's doing and how it's performing. Yeah. Oh yeah, well NLTK is like definitely the go-to for handling any kind of textual information, especially like pre-processing, doing the sentence structure hierarchy that I was talking about, that kind of stuff, definitely that. And well, specifically for sentiment analysis, there's a ton of pre-trained models that exist online that you can just download from universities and stuff, and those typically perform the best. So if you're gonna do that, then I would go with something pre-trained.
Do you want to just talk a little bit? I feel like that's a good example of like a problem about like sentiment analysis is the problem of like taking some text and figuring out if it's positive or negative, right?
Yeah, exactly.
And how you would approach that, and then like, and how it applies to like the bias, like where the bias and variance come into that problem. Just like real quick, high level over like the bias and variance.
Yeah. So I mean, so you have a sentence and you want to figure out if it's positive or negative. So first you have to find a way to represent that sentence numerically, because all machine learning models kind of work as like numerical processes. And so the first thing that you want to do is figure out the sentence structure of the sentence itself, because in determining the sentiment, you have to figure out, okay, what was the sentence talking about, and what kind of adjectives or like how are they talking about that subject. And that can be really revealed in figuring out, which word is the subject of the sentence, and then modifiers on the sentiment of that subject. So figuring out the sentence structure is really important. And then once you've done that, there's like a lot of pre-existing ways to transform that into just a vector of, what sentence part is it, and then what word is associated with that sentence part. But just like thinking of, all the different ways to describe something as bad or something's good, there's a lot of different ways to do that. And a lot of different ways to, write out the same sentiment in a sentence, but just like using different words or different arrangements of words. So instinctively, you kind of already know, like, okay, this is a high variance problem because there's so many different possible data points and so many different like basically ways to arrive at a positive or negative sentiment. So you're going to want something that is not very sensitive to variance in your data, if that makes sense. Yeah, very cool. Yes, sir.
Just a higher theoretical question. This kind of research and technology is sort of in its infancy, right? Like, how long do you think it'll take until it's kind of scary good?
Well, the Perceptron was.
My Yahoo spam filter sucks.
Well, okay, so, I mean, the Perceptron, I think, has been around since, like, the 50s, I think, if somebody wants to correct me, yeah. And so, I mean, a lot of this stuff has been around for a really long time. It's all the kind of deep learning and neural networks that's really been in the news a lot lately and is where a lot of the big advancements have come from. But I think you raised, like, a really good point with spam filters and how, like, they maybe aren't performing well for you because, you know, when I talk about a solution, for like a machine learning task, I'm really talking about things that the model has picked up in the data to recognize that like, okay, this email might be spam or not spam. So, you know, a while back you would get emails about Viagra and stuff like that all the time. So if you train a model on emails back then, it might think like, okay, anytime I see the word Viagra or anything like that, I automatically know like it's spam. But, you know, the people writing that spam will quickly recognize that and then make adjustments so that their spam can make it through the filters. So it's kind of a cat and mouse game, and you know, the like time at which your data was collected is definitely like an important aspect of this process. So yeah.
I think just to sort of add on,
Oh yeah.
one good sort of like soundbite that was stated this year is anything a human can do in about a second, a computer can now do. So if you sort of think about the things that you engage with and have to decide on, anything that takes you about a second to do, a computer can now do that. Anything that's more complicated than that, computers aren't really good at doing that yet. So sort of, if you sort of look at the spectrum of infancy versus scary good, around about 1 second.
Yeah, so what all this is specialized learning. So it's learning that's specialized to the task itself. You know, you can't give a spam filter like chessboard and like have it play chess. And that's kind of like the next step is, yeah. So I mean, you don't, like this stuff is on a completely different level than like generalized learning, which is like the next step, which is being able to learn a task without specific rules on how to learn it, I guess. But yeah, we're definitely a ways away from that, you know. Like chess, well, Go was just solved like last year. They had like an algorithm beat the world's best Go player. So that's kind of an indicator of where we're at right now, I would say. Yeah.
The underlying part of the models, like for these two, for example, like how do they keep track of their learning? Like, are they building databases or are they writing functions for themselves?
So all that a model, once you're kind of done training it, everything, all that. Yeah. So all that a model really is, well, a model I would say is like one, how it learns, and then two, it's like representation of what's learned. So how it learns with the Perceptron is, you know, an iterative process, but really all it's keeping track of, you know, is that one line that it draws. And so every iteration, it just has one basically math formula to adjust it. And then it redoes it every time. So all that's really memorizing is that one line itself, or like that one linear line that it draws. With naive Bayes, it's a lot different. It actually has to memorize the entire data set. No, memorize like the probabilities associated with the data set. So naive Bayes is probabilistic. It's like, you know, what's the probability of this label given this is the data point, you know? And since it's probabilistic, it has to like have memory of everything that's seen more or less. So it has probabilities associated with every single feature that you give it, if that makes sense. But something like deep learning, you know, it learns or like saves its solution in matrices, large matrices that it has to, you know, do a bunch of multiplications through to get. So it really depends on the model, but generally speaking, it saves what it's learned, not in databases, but just as like a vector, basically. Yeah.
That would be the program that you get back to your result diagram and include an output.
Yeah.
You basically just get like a matrix of numbers out.
Yeah, exactly. Yeah, yeah. Well, that's for most models. So any model that like naive Bayes, you don't necessarily get like this nice vector of, well, you can get a nice vector of probabilities out of it, but that's not generally how you save all of it. Yeah.
Is there any fundamental differences between like a text, your inputs is text-based versus images? Or is it really just?
Yeah, so it depends. Well, first for text, it depends on the task that you're working on. So say you're trying to predict, like, given a book, what is the like genre of book, like historical fiction, blah, blah. So you want to be able to first represent that book using the like words in it, but then also really find what words are important and might indicate like the genre of the book itself. So first you have to count all the words that appear in the book, but then there's things like TF, IDF that can indicate based on the frequency of words and kind of where those words appear in the document as like how important they are to the document itself. And then with images, the simplest representation that you can do is, image is kind of a matrix of pixel values. So you could just flatten it into one long vector of pixel values. But then beyond that, if you're interested in object detection, then you would want to apply something, for instance, to like kind of get the edges of all the shapes in the image itself, so that you kind of eliminate all the information that could kind of throw off your machine learning algorithm and kind of focus on the important aspects. Yeah. Mm-hmm. Yeah. Well, for like, yeah.
Okay, so that's really before the
Yeah, exactly. Yeah, all the, yeah.
And in the case of, let's say, a neural network, you're passing through phases of that network, and it's trying to extract different pieces of that image, which determines it's a ball or it's not, potentially. And it's into a score, which are the labels which you talk about earlier. So you're ultimately trying to get a label out of something.
Right.
Yeah. Yeah, I guess what I've been talking about is all those steps after extracting like the piece of information that you find important, Yeah. Okay, cool. Oh yeah.
What's the next step after you burn your test data but you're not happy with the model?
Well, assuming you have the resources for it, it's collect another like set of data for testing. But by the time that you get to the point where you're ready to use that test set on your model to evaluate it, you kind of know that it's gonna produce like a good enough result. But generally speaking, yeah, you just leave it alone.
That sort of brings up a sort of silly point, but isn't model prediction or model best fit a perfect problem for machine learning itself? And that you would use all the models, or if there's a finite set, you would just burn your test data on all of them and say, this is the best thing that I want, and then it would pick your model for you?
Yeah, well, so there are algorithms that do that. It's just not really like an efficient thing to do.
Why not do that every time?
Yeah.
Is there a flaw to predict a model versus a machine? Probably the best one.
I mean, I think like the number one point that comes to mind is that it's just like not really an efficient thing to do with your time. And, just throwing a bunch of models at your data set doesn't really tell you, like you could get a model that performs really well on that data, but is not actually the best model for it because your data might be such that like the model can learn it really well, but in the wild it'll see other data that it just can't handle very well.
But that's kind of honing your algorithm ultimately.
Yeah, well, it's like there's like the actual machine learning process, there's some, like this is just one small component of it, you know what I mean? And even though you could throw like 100 models at the same data set and they could all give you the same precision and recall for it. And that could be because your data just is really terrible, or that it's like really simple and so all of them can learn really well. But just throwing all those models at it isn't necessarily going to indicate why one model is better than the other. And that's kind of where the, the process really happens, is like, okay, I found this model and it's performing really well, but I can't squeak out any more performance for it, so maybe I should like go back and rework like how I'm extracting features for that model. And it's that kind of process, I guess. And I mean, there are, like you could just make an array of like every single model and just loop through it. But that would take, first, a very long time to do it. But probably you could figure out yourself the best model for it before that process continues, I guess is what I'm thinking.
Another answer to that question is some models are not applicable in all environments. So for example, in the classification, some models are really memory intensive, CPU processing intensive once you actually deploy them, and you don't use them on a mobile phone. So there are other models that are much more memory efficient that give up accuracy in exchange for better low CPU performance. So sometimes you're cleaving off based on how you want to deploy that model.
So no matter how good your tuning is, we're still dealing with fundamental hardware issues.
I would say more so now than the hardware.
Yeah.
To certain models.
Because you've got like very exotic hardware oftentimes to try to train these and use these, not computers, desktops, that sort of stuff. Yeah, you're oftentimes limited just by money.
Yeah, and I guess one more point for that is like some models, just the way that they're designed, will be able to perfectly learn whatever data you give it. So you would get 100% accuracy and recall for it, no matter what the data is. But because you're not necessarily in this case like concerned with what the actual model is, only its performance, you wouldn't, like that model that perfectly learns your data would do terribly out in the world.
Yeah, it's very nuanced because you
Yeah.
can say that that's your output and you want that every time, so always choose that model.
Yeah, exactly. I mean, if you're only thinking about precision and recall and during this training process, the best model is just to memorize your entire data set, you know what I mean? But you're not really learning anything from doing that.
Just from perspective, how long does it take to train some, like, for the actual time? Because I know burning through it, like, say, it takes a long time. Like,
Yeah.
you run, like, something you're working on.
So it definitely depends on the data itself and kind of how you have things set up. So typically what I would do is first like figure out all my like feature extraction and do all that, and then run my data through those processes to get vector representations of all my data, and then like serialize those arrays so that, and then like, so whenever I want to test a model, I can deserialize them and just run through it really fast. And that speeds up things. But the actual like training process really depends on the model itself, because like a perceptron, it could never converge on a solution. It can just run forever. And even things like AdaBoost, which is a boosting algorithm, it is kind of designed to run forever. But other things like a linear regression, you can calculate the solution to that in constant time, so it's like less than a second, So it really depends.
And on your data, on how much data you have, right?
Yeah.
And some models also are like linearly like performant based on like
The amount of data that you have.
Well, the amount of data, but also like the size that you scale them up, right?
Yeah.
You're thinking of like how many perceptrons you have in a network or something like. Well, that's not linear. I don't think that's directly, but either way, that is directly related to like the amount of CPU you have. And one easy thing is like maybe it'll be better with like more of that, but then that could be like that.
Yeah.
So you end up hitting a ceiling that's like, well, I can't afford like to go higher. It has to be reasonable, but the answer could be 3 milliseconds to train a model, or it could be like a year. Like it totally depends on what you're doing, right?
Yeah, exactly. Yeah.
Do you have to have like Google's cluster though in general to be good at this, or can you actually be, relatively successful as kind of a small player?
I think it's kind of just depends on what the application. Like figuring out, a neural network to, be a person in chess is going to be a lot more difficult than spam filtering. So it really depends what you're working on. I think unless you're working on something really weird or like, pathological. Somebody else has tried to do it or like has done it online. So looking around, that can give you a lot of intuition on like how hard a problem actually is and what progress that people made in the past.
I can add another specific example. Like I did a lot of image classification, and with image classification, you can start with an existing model that's been trained on millions of images, and all you're doing is trying to take that last layer and retrain on your data set. So you're basically freezing 99.9% of the model, and you're trying to get to figure out your data set. With that, which is called transfer learning, I can do that on a laptop, easily in an hour, and get reasonable accuracy. If I'm doing the entire thing, I need multiple GPUs for a month to train all of those parameters. So if your problem set is already described by someone that's already been solved and you can transfer that knowledge over, you can easily do it with a laptop. So if you can leverage other people's hard work, then absolutely.
I guess one thing we mentioned before about using the model and deploy it. So please take advantage of spot computing. Unless you don't have an internet connection somewhere or you're out in the boondoggle, you couldn't take advantage of spot computing. Just to make that more out.
Yeah, you mean like having a model running on a server as opposed to.
Yeah, so you're not trying to do that if you're on some hardware that can't handle that. Just do spot computing and send it back and Amazon.
It depends on the problem domain. Like some ones they want to classify real time based on what you're looking. So in that case, throughput becomes an issue of your network connection. But yes, if it's something that can be done asynchronously, absolutely.
Yeah, there's also like data considerations there, right? Because if you're going to train on like 10 terabytes of data, then like your real bottleneck is like even if you rent a massive like blob of computational power from Amazon, now you have to send it 10 terabytes of data or whatever, and so like that. All right.
Very cool. Well, thank you.
Cool. I think we're going to take a 10.